Our speaker this evening has 2 decades of massively parallel database experience as well as experience in enterprise storage applications. Please welcome the CTO and founder of ParElastic, Amrith Kumar.
Okay, it works. Thanks, Eric. We'll try the next step so you can see the screen now. So considering all of you know the answers, I'm not sure why I'm doing a presentation. Is there a good pub we could go to instead? Sounds like all of you are people who work with databases of some kind or not. Many of you have probably used tried sharding before. Some of you seem to agree that sharding is not a particularly nice idea. We start by just telling you what this presentation is about. And if you start hearing an echo, let me know. Maybe I'll turn this microphone down. Sounds okay?
Yes.
Okay. All right. So Eric talked about if you have 3G, 4G, whatever. If you want to follow along, you want to read along. Go ahead. Let's start with what we're going to talk about, what we're not going to talk about. Big red sign on the right. I'm not the sales guy around here, so this is not going to be a sales pitch. I'm going to talk about our product, so that's going to be the latter half of it, and I'm going to talk about it mostly in generalities. Okay? Here. Do you hear someone? Would you happen to know where that volume control is? Would you turn it down just one little bit? Okay. So I'm not the sales guy. I'm not going to give you a sales pitch. I'm the CTO, as Eric said. So at any point, if you want to stop, ask questions, dig deeper, happy to get into that in more detail. I've spent a couple of, maybe 15 years working on parallel databases. So if you guys are working on something which is in this general space and you want to talk about that, happy to turn the slides off and talk about that. Right? So, how many of you here have used MySQL? Some of you have not used MySQL. Raise your hands now. Okay. What databases have you used? Okay. No? How many of you have run into problems scaling your database at any point? What kind of problems have you run into?
Basically response time, ability to enable jump, expand,
Okay.
covering the index, indexes, everything else keeps growing.
Basically the same thing. Response time, data storage, when you get big data, you actually have to scale out very, very secure again.
Okay. Lots of data, response time, those seem to be some of the things that you're talking about here. I'm going to be talking about some solutions which try and address these problems. A large portion of this presentation is probably going to be about stuff which you could use, entirely unrelated to our product. These slides are going to be available online. I have no idea where, but Eric will share them someplace. You can go to our company's website and you'll find them there as well. So, without further ado, again, at any point, raise your hand, ask questions, stand up, shout, whatever it takes to get my attention, right? What is the scalability problem? And bonus question, anybody know what that thing is? Greek mythology, anybody? I hear somebody say Hydra. Who? Okay, why?
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 Why is it a Hydra?
No, why is a Hydra kind of appropriate in this case?
Beast, right?
It's a problem with many faces. Scalability is a it's a common problem, but different people describe it differently. Some people describe it in terms of, I have too many people coming to my database and the response goes to shit. Too many people write a query at the same time and the response goes to shit. I have too much data and the response is no good. There's many people who are building applications in the SaaS model. I have too many databases. If you happen to go to Percona, how many of you know Percona Live, London? There's a presentation by somebody about 50,000 or 500,000 databases in a database server. There are people pushing it to some pretty insane limits. You have scalability problems there as well. There's problems depending on whether you're reading the database or writing the database. So depending on exactly what your application is doing, you might be running into a scalability problem. Scalability is not one problem. Scalability is a collection of problems which all have similar results. And those similar results are your customers are not happy, your database server goes down, things like that. As your application evolves, your problem may change over time. It's important to remember that scalability is a problem which you grow with. Over time, it's going to change. You have to use different techniques to address it. So we talked about several things here. I'm going to talk about each one in a little bit more detail. So this picture here, by the way, is real throughput numbers from a site when a couple of years ago, before I started this company, a company which is now a public company. This is traffic on a travel site within several hours. And the peaks here represent some promotion which they happen to announce. Okay. I don't think I'm allowed to mention the name of the company, but it has something to do with boats and things like that, if you're familiar with that analogy. It's the kind of boat you put in the water. Depending on the number of connections you have at any point in time, and these are the results from a benchmark which we did. Response time in milliseconds. Red means bad, green means good. This is not a revenue curve. Higher is not better. This is a response time curve. You want to have short response times. But when you have more users, that's what MySQL is. Now, if you happen to have a promotion and the number of people showing up on your site shoots up like this, how do you size your database? Do you size it for this level? Do you size it for this level? All right, show of hands. What happens if I size my database for this level, this low? Over provision. What happens if you provision it for years?
Losing business.
Yep. So this is a very real problem which people face. So Eric was talking about 20 years of experience with databases. 1991, I used to work for Citibank. We used to make retail banking applications. We used to size them and sell them to other banks. How did we size the database which we used? 3 simple questions. How many branches? How many ATMs? How many tellers? That's it. The number of ATMs and the number of tellers tell you how many transactions you can have per second. Maximum. Number of branches tells you how long your batch window is going to be. That was enough to size the database 25 years ago. Today everybody's got a phone and a banking app. They do banking from the web. Banking apps see this kind of workload change. So what level do you provision to? So it's a hard problem to solve. You talked about data retention, another benchmark which we did. This way, by the way, this benchmark and this benchmark, you can do this stuff yourself. The benchmark in question is standard sysbench. Sysbench OLTP, standard MySQL and Amazon. What did I do? I ran sysbench OLTP with different data volumes. How do you change the data volume? Change the number of rows. That's your response time curve. Now, if you are a company which is managing to sit at this place, your response time is wonderful, but you don't have a big business. You want to be in this side, but then your response time goes down. How do you solve this problem? these are very real problems which people are facing. And why is it kind of important that you have a lot of data? You talked about big data. The most common thing which people tell us is, we need to retain data for a longer period of time because there's a value in having this data around. Data for what a customer did 2 years ago or what people's shopping trends were 2 years ago is important to us. Key clicks from 6 months ago are important to us. That's a common data. How do you keep track of that? Somebody mentioned indexing and things like that. So this is probably what you were running into. And this explains this curve here. Maybe well-known fact, maybe not so well-known fact. If you keep all your data in memory and all your indexes in memory, MySQL is a blazing fast database. Yeah, it depends on the query. If you want to do a wacky join, yeah, sure, absolutely.
The temporary data is still used, right?
Hold that thought, because we have the sales pitch part, which I don't want to talk about. We'll tell you something about. The non-sales pitch, sales pitch, yeah. If you can't keep all your data in memory, keep your indexes in memory. If you can't keep everything in memory, you got a problem. There's a lot of people who will try and spin this picture to you a slightly different way and tell you, memory is getting cheaper. Sure, it's your credit card. Memory is getting cheaper. It's still a whole lot more expensive than it is. Solid state or otherwise. You can't put everything in memory. At some point, you're going to have to persist it. There's a very well-known database company from up near Boston, which tried to tell you that there's no need to put stuff on disk. Keep everything in memory. Keep 2 copies in memory. Yeah, you got to get it on disk at some point. Okay, how many of you here are building SaaS applications? Okay. If there's 50 people, 2 people who raise their hands, so I'll ask both of you. 3 of you raise your hands. If you have 50, 100, 1,000 people who are using your SaaS application, do you give each one a database of their own? No? 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 Okay, smart. The easiest model is the model on the right, and you probably are not doing that because this other benchmark also says bench. As you change the number of databases on a single MySQL server, that's your response time. By the way, when did you guys not use one database per tenant?
You really want to go into it?
Sure. This is not only about my talking. I want to learn something from all your experiences.
I don't think this is one perspective of code dispatching, but basically allows you to dice and slice data very quickly when you want to actually use that data elsewhere. That's in most of these SaaS businesses. We give the product away. The users are the product, and so in order to sell that back-end data, you have to escalate that data space much in any different way, depending on location, pricing, gender, all sorts of things. Having it in one database is just easier to do.
Do you allow the people who use your application to customize the SQL which is created and which is sent to the database?
Well, in a way we do. What we allow is by selection of different features and things we're doing, we build queries on the fly.
You build queries. You don't allow people to write SQL.
Now, actually, like allow blind people to drive in the past.
Are there other clients? That's wrong here.
You want to let people lose their SQL on your business, you might as well just blow your shop.
Yeah, there's one other reason why you may not want to do that, because you have everybody's data in one table. And you're probably sticking filters on to make sure that a particular tenant only sees his or her data.
Well, it goes further than that. I mean, then there's a lot of how do you flatten tables and put offering tables on the front end and flatten, pick up tables.
Yep.
There's all sorts of tricks and games you can play, or I probably for
Sure.
hours on end, but I'm sure you know most of it.
Yeah, well, many of the things which you're talking about, and this goes back to maybe a different thing for other people who are planning to do this to think about. All of the things which the gentleman talked about are good things to do, but they're in the realm of database research. And if you're building an application, how much of your R&D time do you want to spend on that database research? Yeah, he's saying 0. I agree bunch of time on it. And if there happens to be a solution, so for instance, this one, which does all that stuff for you, wouldn't it be nice? So, a very simple, huh?
That's why I'm sitting here.
Okay. One very simple design paradigm which people use when they build SaaS applications is to give each tenant of the application their own database. Very simple paradigm. That way the application is very simple. When you connect to the application, you provide it username and password, you translate that with one simple lookup table and say, oh, this gentleman goes to database number 72. And beyond that point, he has in database 72 his 110 tables, which are part of the application schema, and he will never see the next person's data. Unfortunately, what that means is his database lives on one database instance, which lives on one server. Your business started selling flowers. When's your most busy day?
Sunday.
Okay, most busy day of the year?
February 14th.
Mother's Day? Somewhere around there? Okay. So, your business's database is living on this server, and yours is a very successful business. What do you think happens to that server on Mother's Day, or the day before Mother's Day?
The plans could crash.
It gets its butt kicked is the technically correct answer. What happens to all the other people whose databases happen to be on the same server? They got a denial of service attack. Thank you. But that's exactly the problem which a lot of people run into. It's called the bad neighbor effect. If you go down the path of building a SaaS application and you use a model where you give everybody their own database, okay, either you hope you don't get successful because this is your response time curve, or if you happen to get successful, you're going to have hotspots. And this problem has been solved. The cloud service provider is happy to tell you. It's very simple. Run your server at a utilization of 5 to 7% most of the time. Also known as over-provision the living daylights. Not a very good idea. One of our customers, we've been working with these guys for a long time, that they could not put more than 1,000 consumers on a single database server at any point in time. They're incredibly successful, but those servers are running at 5 to 7% CPU busy at any point in time. Because God forbid, Mother's Day happens. Not a clever way to do it. Okay. One of the common other problems which you have with databases is, databases like MySQL especially, is as long as you're doing simple selects and not doing any fancy joins and stuff like that, and you can keep all your data in memory, MySQL is a wonderful database. Okay, you want to start doing more fancy things. You want to start doing writes. MySQL's performance often tails off very, very quickly. Start throwing more complex queries at it. That's going to give you some very, very serious hardware. How do you go about scaling this? It's easier to scale reads, of course. You have memcached, you have other kinds of caching. There's many other kinds of solutions for read scaling. Akamai is a wonderful thing if you get big enough. But what if you're doing a social network? You were talking about doing a social network. Social networks are all about, surprise, social interactions. If I have a website which is read-only, or the vast majority of people are only going to read it and there's going to be a small number of people who are posting content to it, yeah, scaling that site's much easier. Scaling a site where you want people to interact is a much, much harder problem. How do you scale rights? And with that, I think I'm going to take just a pause for a second to say, are there other kinds of problems any of you would face which you would generally call scalability?
Yeah, and the notion of eventual consistency, which is tied in easily with the problem. Even if you're running your read, multi-master, multi-slave read, you still have the transition time that slave read and you get consistency. So someone may see something where one database is
give you the ability to distribute load across multiple servers, but when you write to one, it takes a while for that data to propagate to all of them. So how many of you have ever looked at a website where you've noticed people have posted the exact identical comment twice back to back? How many of you have ever done it when you posted a comment and you've noticed your comment's missing and you posted the same bloody thing again? Thank you so much. You're the kinds of guys who are running into this problem. If you post a comment to one place and your application allows you to write it to one place and subsequently renders your page by reading from another where that data hasn't yet made it, your user is going to say, hey, my comment didn't make it. And you paste the same thing again. Perfectly normal. So it's a problem with the database, and that's something which hopefully we can help you solve. So this all seems like very basic stuff, right? So at some level, it's kind of useful to look back to how we got here, because sometimes it's a little bit surprising if you look at how we got here that it's pretty surprising that we even did. So anyway, the first major reason we got here is, and I believe there are three. The first major reason is that applications usage has changed dramatically. So there used to be a time when news cycles were 1 day. People would listen to the news once a day and they were happy. Today you get news updates like a minute. The cycle on which things are current, hot, gone is now measured in minutes. If you're building an application and you can't keep up with that, well, your application is not going to be very popular. At least it's not going to be popular for long. The second is that, and I remember this from the early 2000s, if you wanted to start a company and you wanted to raise money, you ended up raising $5-7 million because the first thing you would do was go and set up a data center. Everybody had their own data center. Everybody had PCs. Everybody had servers. Nobody does that anymore. Computing is ridiculously cheap. The cloud has changed all of that dynamic. You can get computing on the cheap, but not all problems are divisible in a way in which you can utilize them. So think about the many tiers in your web stack. Your application tier may be scalable. Your web tier, absolutely it's scalable. Your web farm, if you get a big spike, spin up more web servers. You can't really do that with your database. So if your solution can scale up, it's going to win in this cheap commodity market. If your application cannot scale up, it's going to be toast. And the last thing is, and we'll talk a little bit more about this, traditionally, if your database is able, and this goes a little bit back to maybe the evolution of CPUs and stuff like that, there was a time when you had 66 megahertz, then you had the gigahertz, and then the 2 gig. And the promise was that it would keep going on and on and on and on, where one core would go faster and faster and faster. Well, nobody's figured out how to change the speed of light yet. Nobody's managed to figure out that, or managed to change the fact that your power dissipation is going to be based on the square root of frequency. You have not seen a chip faster than 3 gig in the commodity market in a long time. Commodity market.
I was going to say E-Wave just the series expansion that have conflict.
Well, yes. So let's say, when you can get MySQL running on one of those, just give me a call and I'll be happy to let you know about how that works out. Because with that, with quantum computing, your response time in theory is 0 because somewhere the answer is already there. So you don't have to bother with this query processing. All answers are there, absolutely. And the data is already there too. Absolutely, it's gotten smaller and smaller. The materials have fundamentally not changing? Absolutely. So if you build a database, and MySQL is, by the way, MySQL, Oracle, and all these databases were designed a while ago. If you had a 20 gigahertz processor, MySQL is a great database for you. It'll solve all of your problems for you. But that many gig processor is kind of short supply. They're out of stock. So if you're not able to use higher core densities, your database server is not going to be as effective. Oracle, of course, does a better job of this than MySQL, but MySQL is getting there slowly. But over time, there's also been another trend with databases. I guess this is going to date me a little bit, but over time, as databases have evolved, not only here, but actually written a program in COBOL. Raise your hand. Okay, good. Long ago, when you wrote programs in Swift ISAM, your app knew the underlying data structure absolutely completely, exactly like it is today in NewSQL. But some guys in lab codes decided, they had a good reason for this, that a layer of abstraction between your application and the data store and a query language in the middle is a good thing. It actually is a very good idea. So you have a swing from XISAM-based applications to RDBMSs. RDBMSs did a lot of good things for you, but as programming languages evolved, people wanted this notion of an object, and they wanted to project the object into the database. How many of you have a T-shirt which says object databases are going to rule the world? Some of you have probably seen it. Some of you have gone to the conferences, maybe. There was a time when people said object databases will rule the world, relational databases are dead, don't bother reading about them anymore. Nobody lists an object database on their resume. In the early 2000s, when I first started to see parallel databases, OLAP queues were all the rage. RDBMSs could not do high volume aggregations. They had a big data problem at that time. Big data at that point in time was a gigabyte of data. And they couldn't do aggregations fast enough. They had to pre-compute cubes and aggregates. How many of you ever learned a language called MDX? Great. I have the T-shirt which says MDX is going to take over the world. All right? Hey, there's somebody there who actually learned MDX. Yeah.
Yeah, actually, when you do SQL, Microsoft SQL Server, or they have to queries, you have to run MDX.
Absolutely, that's right.
Multi-dimensional queries, so you can have multi-dimensional dimension.
Exactly. Parallel databases today can do the exact same thing for you on raw data without you having to pre-construct the queue. We're seeing the exact same transition again, where people are identifying there's a problem with relational databases. The damn things don't scale in the cloud. They don't scale in virtualized environments. You make a lot of sacrifices and compromises, and you come up with a good solution, like NoSQL. In my humble opinion, we're here. We're swinging back here. And what I'd really like to know is what's the next one. Because if you know what the next one of these is, you know what the shortcoming is in today's relational databases. But the reason why this particular transition is kind of interesting is the traditional relational database was built for scale up. To get yourself a 20 gig processor, MySQL is a wonderful database for you. Unfortunately, it's not built for scale up. That is the crux of the problem you have with scalability today. And your application is evolving way too fast. These are application dependents. This is the database community's response. Not fast enough.
And I'm sure this will resonate with you as well. Back in the good old days, there was a language called Lisp, and machines called Lisp machines, and a framework that was essentially set up to do the computational intensive
Yep.
issues that on CPU with software are actually being done basis a little more higher. You actually got scheme games and the information list that actual comparatively functional language.
So, you know where you're talking about this particular part of the curve, right? Let me tell you about this part of the curve here, a company which I work at called Netezza. did all this processing on FPGA. Same technologies you're talking about. What are we doing here today? We're doing it in GPUs.
Right.
There's nothing new here. This transition back has happened time and time again.
The fact that they changed the diet.
Today it's expensive, but the price comes down. And more interestingly, CPUs will eventually catch up, and you may not notice that distinction.
Also, GPU is also better than, it depends what kind of problem you're trying to attack.
Absolutely. Yeah, it's not, there's no one solution to all of these problems. Exactly. So, if you are trying to do parallel computing on a GPU, there's a good friend of mine who moved from Boston to Seattle, and he's working on some very, very advanced silicon for GPUs, where he's trying to do parallel database computing on the GPUs. And he's getting some excellent results with Postgres. So, for parallel computing, GPUs are very, very good.
So that's the one caveat. One, the memory is too limited, it's 8 gig, and also the power consumption. If you can put like an ARM into a GPU, it will be much better.
Absolutely, you're right. It's an evolution. You're talking about memory size and speed. Here's the history lesson. You're seeing CPU speeds evolve here on GPUs exactly the same way as you saw them evolve in CPUs. So basically, databases were originally, the architecture for a relational database was created sometime around here. CPU speeds were expected to go forever upwards. It was perfectly fine to have a monolithic architecture. Unfortunately, CPU speeds are now capped. How do you solve this problem? That's basically what we got. So we tried several things. Oracle RAC tried the shared disk. Others have tried the shared everything approach. Unfortunately, these don't scale very well. The most important reason for that, at least with the database, is you can pay twice as much for a server, but that's not going to give you twice the database capacity. It may give you twice the MIPS if you can use it. Maybe not twice the database capacity. Okay. The last of these pictures, I promise. How many of you are familiar with TPCC? TPCC, the benchmark. Okay. TPC is a standard benchmark. It tries to give a representation of a very simple business, a schema consists of 6 tables, and it does some standardized transactions. They include joins and sorts and aggregations and all these fun things. And they try to measure the power of a database engine. So some guys from State University of New York, they took 5 different Amazon RDS instances, and they ran TPCC on all of them. RDS is nothing more than MySQL offered as a service by Amazon. You pay twice as much when you go from a 2x large to a 4x large. I don't think the bar went up. It actually came down. You don't need to run a benchmark, but okay, these guys are at Sunny Stony Brook. They have to run them. Hey, I run benchmarks too. I'll show you all the pictures. This is my one. But the fact of the matter is this. Getting a bigger server for your database is not the answer. You need some mechanism to scale such that when you have more data, when you have more transactions, when you have more stuff to do, you can get a constant response time. To get a constant response time, you need to have more database capacity. So the question is, how are you trying to do that? Here are some solutions. Again, before I move on, is that a typo? No, this is the right text. Questions, comments? Okay, I'll keep going. Stop me if you want. Several strategies to solve this problem. Again, we're going to talk about each of these, so just move right forward. I have seen several people who have told me, we don't need no stinking scalability solutions. We're going to cache everything. We're going to be all good. Image use courtesy of statements. So, to disprove that, we did this little benchmark, of course. You know, you got a nice show people actual data to explain why. So what we did was, we did the same sysbench benchmark, and we implemented a cache. We implemented it using a CDN, and we ran it straight against the database. Again, response time in milliseconds. More is worse. If you can go against your CDN, and it's read-only, and that works fine, you get wonderful response time. If you can't hit your CDN and you have to hit your cache, you still get pretty good response times. See what happens when you hit your database? Caching may be a solution for some problems. Caching is only good for reads. You cannot cache writes. Most social networks are write-heavy. Most importantly, they're personalized. If you log into a website and you are a frequent visitor on that website, and the website identifies you as dear visitor and shows you the same stuff each time you go there, how many times do you go there? Maybe once, maybe twice. On the other hand, if you go to everything, including Flipboard, my account on Flipboard knows who I am and doesn't show me the same article twice. People who are serving ads don't want to serve you the same ad more than once. Caching is not always the answer. It's good for some things, not always. Okay. This image made more sense in Harvard when I did the presentation because the Thinker statue is actually right outside the building right here. I'm just going to get a bigger server. And we hear this regularly from people who say, I'm going to get a bigger server. And some of them have now gone up to the cluster compute servers and they've still on Amazon, and they've still not managed to solve their problems. And now they're considering, okay, so maybe Amazon's not the answer for us, and maybe we have to go and get our own data center, and that's a whole different set of costs. What are you going to do if you can't get a server big enough? And this is a very real problem for a lot of people. If you're not able to partition your workload across multiple servers, how are you going to get a server big enough? Not always possible. My favorite slide, because I love sharding, I think it's a wonderful concept, at least in theory, but I think it's not. A lot of people believe that sharding is going to solve the problem. How many of you are familiar with sharding? I remember I asked the question, some of you raised your hand. The rest of you who don't know about sharding, you can read that later and laugh about it. Sharding, in more seriousness, is a kind of technique where people will partition your data across multiple servers. For example, if your business is logically divisible into 4 regions geographically, let's say I have 4 databases, North database, South database, East and West. And I will vary some logic in my application so that whenever a query comes down, I will send it to the correct place. Okay. You guys with me so far? Okay. Someday I have to go back. I don't know why people like that. So, I am running a sharded database. Please tell me who the best sales guy in the Eastern Zone is. Somebody want to tell me how this will work? What happens? I have a sharded database, sharded geographically, north, south, east, west. I have 4 database servers. I want the best sales guy in the East Zone. What do I do? East Zone, send it to the East server. Fine. Good? Okay. Find me the top 3 sales guys in the East Zone. East Zone, top 3 server, send it to the East Zone, give me the top 3. Give me the top 3 sales guys in my company. Okay, now what happens? So there's a lot of people. There's a very, very well-known company which did a Percona presentation a couple of years ago where they talked about all the wonderful things that sharding did for them and how they implemented sharding, and they went around the world doing this presentation. Great. Then they came back the next year and they did another presentation. It's also about sharding, but they changed the presentation a little bit this time. Because they implemented sharding, their business was able to grow. It was a SaaS business. Initially, they didn't know how to make money. their product, and then they figured out, here's how we're going to monetize this site. And some guy came up with a mechanism to monetize the site. And the guy asked the question, who's the top 3 sales guys in the country? And their sharding solution couldn't address it. They took 1 year and several $1 million to implement that sharding solution. It helped them grow a little, but then they had to do it all over again.
They needed multiple shards for every row.
They needed shards, they needed queries across shards, and all this kind of stuff. And they went and implemented all that. That was their second presentation on how you do Crosschart Operations and all that. And the guy ended the presentation by saying, if we had known this was coming a while ago, we'd have used some other solution. We basically implemented a database on the cheap for our application, and now we're stuck supporting the database. Because if you think about it, you've now got in your application code, which is going to intercept the query coming down and say, oh, is this east zone or west zone, and send it to the right zone. And tomorrow somebody adds a no zone because you happen to go to Mexico. And then someone comes along and says, give me the top 3 sales guys in the South American region. What zones are those? Yeah, now you have to start, you just have to start it. You basically build a house of cards, and now you're building a house of cards on top of the house of cards. So,
Sharding is just another bad form of partitioning, which is static.
yeah, it's a static partitioning mechanism which gives you silos of data. But there's a nugget of truth to sharding, and that is, when you have a lot of data, my database doesn't scale. How do I solve it? Have many databases, each with less data. Good point. On the other hand, now I have many little problems, all waiting to grow at their own speed. And then the north zone happens to grow faster than the east zone. Now the north zone is a problem. What the hell do you do with that zone? You gotta split the shard. So, I think when the guy came up with the term sharding, he thought about it in a different way, but it literally is a bunch of pieces of glass which will cut your hand.
It's funny that you put the glass in, but when I explain it to people, I'm like, imagine, when they say, when missiles coming in, and they have got to go up and shoot it down, it's like, okay, you just shot it down, where are all the pieces going? You're going to shoot down that airline, but it's, now you got millions of pieces.
You got a lot of little pieces of stuff. And the problem with sharding is you've got silos of data, and you have a management nightmare in your application to try and put those pieces together. Okay. So, of course, there's a lot of people who have these other newfangled solutions. Several hundreds of years ago, people had newfangled solutions as well. We used to sell them. The fundamental problem with a lot of these solutions, whether it's sharding or whether it's a NewSQL solution, is you got to rewrite your application. So most of the NoSQL solutions have no query interface, which is no structured query interface. They have an API. There's no standard API. You talked about benchmarks. Yes, I actually have counted. There are more NoSQL flavors than there are Ben and Jerry's flavors. But if you are attempting to choose a NoSQL database, choosing the flavor is left up to you. And it's not as easy as saying, I usually like vanilla, vanilla is good. If you choose the wrong flavor, and you go implement your application against, I don't want to disparage any particular one, so just start a pull-up, pick any one, and you find that it doesn't do what you want, you get to re-engineer that all over again for the next interface. This must be my fault, right? How many of you are familiar with what ACID is? Okay, good. So I don't have to tell you about it. Most NoSQL databases don't provide you ACID. They generate ACID. Yeah, different kinds of ACID. Some of them now are trying to do ACID. In fairness, some of them are trying to give you some parts of ACID. Some of them claim they do ACID because they say ACID only says consistency. Eventual consistency is also consistency. Yeah, sure, whatever with that. But if you have a standard application and you have a bunch of people who already know a language, this is the lot. And it probably isn't going to solve all of your problems. I'm firmly a believer that there's a place for NoSQL in the world, like there was a place for object databases, and like there's a place for OLAP cubes. By the way, anytime you book a hotel room, everyone here has probably booked a hotel room at some time or the other. An object database probably is the one to store your reservation. At the end of the day, 20 years later, for some reason, people have found that object databases work really well in the hotel reservation business. It got relegated to a niche. Probably 20 years from now, snake oil guy is going to be relegated to a niche as well. So, somebody talked about other ways of solving the problem. One is this read-write splitting. How many of you are familiar with this idea of read-write splitting? No? Replication in general? Scalera? People use Scalera? Yeah, okay. So
the off-the-shelf things don't cover all bases, so you can write your own secret sauce.
yes.
Secret sauce and serve yourself. So that's going to be more work. Talking about the guys who are in it.
Well, there's a bunch of people who consider that to be job security, right? So there's a lot of solutions out there which try to solve this problem by saying one database is not able to handle all of the load. What's the solution? Well, many databases all with the same data, and they will distribute the load. So if there's 50,000 people querying the database, and I have 5 copies, 10,000 to each database. Very nice. Math works very good. Somebody tries to write to one of the databases. Okay. That's the problem you get. You're trying to write that stuff to the other 4 very quickly before anybody tries to read it. And it takes some amount of time for that to make its way over there. Now there's a replication lag, replication breaks. Somebody writes the same record in multiple places. There's a conflict. All this is left as an exercise of reader to fix. The people who don't want to have the split problem, the issue of replication breaking, they split reads and writes. Also doesn't solve all the problems. It scales. Replication scales reads. Yeah, 50,000 people reading it, 5 databases, 10,000 apiece, works great. Does not scale writes. Read-write splitting gives you better reads, but you get replication lag to deal with. So you still have to solve the problem. How many of you have heard of MySQL cluster? Okay. MySQL cluster is an offering from MySQL. It's MySQL sitting on top of their NDB storage engine. NDB is a key-value store-based storage engine. You cannot use any other storage engine if you're using MySQL cluster. It's only the NDB storage engine. And primarily what it is a distributed key-value store. Okay. There are published benchmarks about how blazing fast MySQL cluster is. Read the fine print, please, because all those benchmarks talk about this Flex async application, which communicates with MySQL cluster on the NDB interface, not on the SQL interface. Nobody gives you SQL benchmarks. And oh, by the way, the benchmark is also read-only. So, I agree that the benchmark says it can do 1.2 billion transactions a second. But yeah, those 1.2 billion transactions a second, you could probably do with a Post-it note in that hand. Read the fine print. So, personally, I think there's a different way of solving the problem, which kind of takes aspects from each of the things which these earlier solutions have talked about. Fundamentally, all the solutions have one thing right. Relational databases do have a problem with scale. Scaling up is not a solution. You have to scale up. But at the end of the day, you want to have a standard interface, and you want to scale up in such a way that you can use many servers at the same time. So parallel databases have been around for a long time. For those of you who are into reading academic papers, footnote tells you what the paper is. But several companies have actually built very successful products on this architecture. This is not some fancy new science project which we're talking about. Shared nothing, I hope the term's familiar to everybody, but if it's not, happy to tell you what that is. Yes, no? Shared nothing? Okay, so computer science term, there's three kinds of systems. One is shared nothing, one is shared disk, the other is shared everything, there's shared CPU as well in the middle. It's basically a term for cluster computing, and it says what aspects of the computers are shared across the cluster. In a shared everything system, all aspects are shared across all machines in the cluster. A shared disk system, something like Oracle Rack. The disk storage is shared, the compute infrastructure is not. In a shared nothing system, nothing is shared. It's free-running computers which just collaborate over them. How many of you here are familiar with MapReduce or Hadoop or any of those kinds of things? Okay, Hadoop and MapReduce are another concept, another implementation of shared nothing. Behind the scenes, they're storing data on HDFS. That's an implementation convenience, but it's still a shared nothing application. So, how do you execute queries in a shared nothing system? The picture, by the way, I'm sorry if it's a little bit small and you're not able to see it, but it is in this paper here. Your data is stored on these little cylinders at the bottom. You partition the data over multiple cylinders, multiple database instances. Whatever database operations you want to perform, which can be performed in parallel, you perform them in parallel, and then you perform some set of merge operations in one place. Give me the top 3 sales guys in the company, north, south, east, west. Give me the top 3, top 3, top 3, top 3. The merge operation does the bubble sort and gives you 3. That's it. To the guy sitting up top who asked the question, give me the top 3 sales guys in the question, he gets 3 rows of data. It doesn't matter to him that the data is stored in 4 different places or 40 different places. He asked the question, give me the top 3, he got the top 3. This is the architecture behind it. So, why is all this stuff useful? This is the bullet points. We're going to talk about these in more detail, so just quickly run through them. Linear improvements in reads and writes. I'll show you some graphs about that. Better than linear improvement in joins. Joins, remember, your join performance usually goes up if you're not able to get the full benefit of indexes and things like that. It goes up based on the product of the number of rows in the A and B tables. And if you're doing sorts and you're having less data to sort because you're doing it in parallel, you get better than linear scale sort. So we'll look at some of these in more detail. So a common comparison, again, we made this analogy before as well. How's parallel database is different from sharding? The primary difference is the first one. Sharding is an application architecture. You build stuff into your application which ties it to where the data physically resides. Parallel database is a database architecture. The application is not constrained by the parallel architecture where the data is. The application ends up being constrained by where the data actually is. And depending on your application, maybe you can't even shard your data. So, let me pause for a second and see if there's any questions and whether I've lost all of you or whether I should start throwing rocks at you. Questions? Comments? Eric? No, I have a couple now. Like about 26 more slides. Actually, exactly. We're at halfway point, so to speak. Yeah, if I said that and everybody got up to leave, I'd have got again. No.
I mean, it happens. I'm sure that talk about has segues whereas ParElastic is spectrum.
Oh, you should ask that. Let me check if I have some slides about that. Well, I'll cover it next time. Yes, we do. So what do? We tend to look at ourselves not so much as a parallel database architecture only, but more as a view of virtualizing the database. Our approach is basically to virtualize the database to solve the issues of scale, of elasticity, multi-tenancy, and things like that. Again, we do it with standard databases. We're not implementing a net new database. Okay, sales pitch is over. So Somebody here mentioned something about temp table performance not being good. Who was that? You, right? Okay, so that was the time I should remember to tell you about this. Big block diagram of what we do. So that's your client app up top. This big box down here is our software. Our software runs somewhere in your cloud, I don't know where, on some machine somewhere. Under the covers, your data is stored on, in this picture, 4 MySQL servers. It could be 4, it could be 15, whatever the number happens to be. Just to be clear that this doesn't mean you need to have 4 machines. I put these 2 on the same server, I put these on their own server, I put these on one server, something like that. Some collection of machines which you happen to have on. We store a portion of your data on each of these servers. So, how do we know which portion of the data to store? You tell us. Similar to what you would do with sharding, where you pick a shard key, you tell us how to distribute the data. At the time that you create your schema, you tell us that. One time only. After that, we'll take care of storing data in that way. Your application comes along and asks a question. Give me the top 3 sales guys in the North Zone. And oh, by the way, I distributed data by zone. My application stores, ParElastic stores, in our metadata. Your schema and the fact that you distributed data based on zone. It takes a look at your query and says, oh, top 3 sales guy based on zone. And the zone is the North Zone. And the tables are partitioned based on zone. Oh, the North Zone happens to be here. We'll send the query here, get you the result, you're all done.
So I have to solve the problem of the metadata getting big for the server that's on.
The metadata literally is just the catalog of, what are the tables, how many columns do you have, that kind of stuff. You would have, in theory, for a single table, the metadata is like under a couple of kilobytes.
Or like a data table.
Doesn't matter how big the table is. It's literally, this is just literally think about it as the DDL goes here. We have a table called tables. The tables table has a list of all the tables you create. We have a table called databases, which has a list of all the databases you create. We have a table for each table's columns. Those of you who are familiar with Postgres architecture, PG underbar, all of those tables.
Which version of MySQL you running? Which version?
Any version that you want. As far as we're concerned, we're looking at MySQL just as it's a database. So right now we're doing only MySQL and work with Oracle SQL Server and Postgres because at the end of the day, it's a database. Long ago, before we formally started shipping the product, we could do heterogeneous multiple different databases. Right now we don't support. At some point in the distant future, maybe we will. So how do we solve the issue with metadata? Yeah, the metadata does not grow proportional to the amount of data in the table. It is literally, that's your DDL. The vast majority of that is cached. So that's not going to be a bottleneck either. So give me the top 3 sales guys in the company. Okay. We look at the metadata and we say, oh, this data is distributed onto 4 nodes by region, and you want the top 4 in the company. Okay. Top 4, top 4, top 4, top 4. Okay. Now I have 12 rows of data. Somebody's got to put the 12 rows of data together. Well, guess who can do that really fast? MySQL. So the reason, there's of course the question which says, why did you pull the 12 rows of data up here and then just pick the top 3 and send them up? As a very clear line in the sand, we do nothing in database time. We receive queries, we execute queries. We don't actually do the database process. Company which I used to work at tried to emulate Oracle by doing all the things which Oracle did in their code. losing proposition. Company went out of business, by the way, after burning through like 50-something million dollars. How many of you have gone through the transition from MySQL 5.0 to 5.5? Okay. What did MySQL change between 5.0 and 5.5, which made a lot of people's heads spin?
From my point of view, we only got burned on a few things that get deprecated.
Now, this isn't a deprecation issue. This was an incompatibility which they did. Okay. You probably haven't worked with data which is multinational or multi-language. Okay. They changed the collation. Okay, so if we were to build the logic to pick the top 3 in our code, we will be fighting we will asymptotically approach MySQL's behavior but never really achieve it. Okay? Who can do MySQL's collation sequence right every single time? MySQL, yeah, right. That's available. So how about we spin up a bunch of nodes and we call these empty. So there's no persistent data on there. I get a spike in traffic. Spin up more. You got enough, sir. There's a guy here. So the way in which the topology matches. Did you see these slides before? You have not been paid any money to ask these questions at exactly the right time. So here's how we do this. We work private cloud, public cloud, Amazon, joint, what's it? OpenStack, not OpenStack. How do you provision a new server in Amazon? There's an API, a RESTful API. How do you do it in joint? It's a little bit hard. How do you do it in some other cloud? You make a phone call. So what we did was we came up with an abstraction where we said we will evaluate from time to time the utilization of the pool of dynamic resources, and if we need more, we will make a call out via a plugin to go and provision more resources. The plugin for Amazon could be configured to go and spin up this node based on an AMI which you have pre-chosen and based on your access key and your secret key, which effectively means your credit card. And it will tell the topology manager when it comes up that I'm a new dynamic node, and he'll be added to the happy family of dynamic nodes.
And is that available, like, the parametric state that in some sort of file or something like that?
That is a policy file which will define how many minimum, how many maximum, and we have some smarts which say when did we spin up the server, you've already paid for the hour, which one do we want to spin down when the utilization comes down, all of those fun kinds of things.
And we can tie it into some AWS CloudWatch stuff.
We have not done any of that. We have not done the AWS CloudWatch part of it. For most people right now, the thing which we've been doing is we've been using a provider which we call a static provider, which is nothing more than a text file with a list of IP addresses. We have the smarts to do that, but the place where people see value is not in the micro-optimization of when they spin up and spin down servers. So people have been more focused on other parts of it.
Yeah, and simply that you guys can address rationalizations in the same procedures as more and more people are getting to where I've been asking because dynamically works this way. Personally, I don't know anything about AWS internal, so even if I need it nowadays, I still may not make that mechanism. So what I really want to say is I have X number of TPS, I have X number of dollars, I have X number of performance I need to see. Give me this, I need this guarantee.
Yeah.
Make this happen, and I want to walk away.
So we have not solved that problem because that is a problem which is infinitely harder to solve. Because what you're asking us to solve is to predict two things. One, what is your future traffic going to be? And second, what is the deterioration in your application or in your database's response when you see said predicted future traffic? I'm happy to predict one.
Right. The second one is very hard.
The second one is very hard. We'll leave the second one. I find it hard to predict even the first one. So if you're willing to give me the hint, I'm fine.
First one, you just put a finger in the air and kind of see what it is. The second one is like, how bad is the color? And that's like, okay.
Actually, I'll disagree with you for one reason on that. So here's our observation on that. We implemented this entire mechanism to automatically scale up and scale down. The real person who has the knowledge of when the spike is going to come is likely this year. So what can we do? We can look at utilization of these servers. We can look at query rates coming in here. Unfortunately, by the point in time that we try to put in hysteresis and all that kinds of things and debounce that, the spikes already hit us in the face and response time's gone out the wrong side. At that point, spinning up the new nodes is probably too little too late. So we kind of spent a little bit of engineering effort on the plugin manager and so on, but we kind of have figured, yeah, we have enough of that for now. That's really not the thing where value is going to come. The value is going to come from the guy saying, there's been a shooting in DC, spin up servers now. Or we're going to be doing a promotion tomorrow for which we expect there's going to be a big uptake. Be prepared for it. Oh, in that case, it will provide provision to more.
But your point is valid. I mean, if it's a human interpretable act,
Yes.
it's up. But to your point, it's like the spike is, over 0 time. Yes, you need infinite power if you have it, if you have a gen, if you have somewhat of a exponential growth, you might be able to.
We might be able to. You're absolutely correct. We have not solved that.
And I see that that's not the right problem. I'm not looking for, some of your site was mentioned on, something, whatever, and 5 minutes later, everyone's saying, or some wrong start.
Yeah, absolutely.
That's the problem that's really makes it possible to solve.
That's a very, very hard. Actually, we have a solution to that problem at a different scale. Not in this presentation. That's the sales pitch, and I'm not going to do that here. We can talk about that afterwards. But I wanted to keep this presentation to be more on the technical side. There's more of a vision side that goes into which I'm happy to touch upon briefly towards the end if you will. There is a solution to that, and we'll talk about that. But anyway, the basic idea is this. At this interface up here, what the application sees is one database. Where the data is stored, who processes the queries, don't worry. Partition the data north, south, east, west, partition it by zip code, don't worry about it. Ask the query, get the answer. The physical representation shouldn't bother the application. Okay. How do we actually distribute the data? 3 ways of distributing it. A couple of you have asked me already, do we just distribute the data or partition the data or whatever it is? Let me point out, we have a distribution model called broadcast. And broadcast basically maintains a replicated copy of data on all 4 nodes. Very useful for lookup tables. The lookup from zip code to city name, not going to change often. Very often used in a joint lookup. We do replicate those things. What we guarantee is collocation of data. If you distribute data based on zip code, then everything for a particular zip code shall always land up on one server. Oh, very nice. Here comes the hard part. I start my system off with 4 servers. And I get really, really, really good traffic on my site. 4 servers is not enough. I want to add a server. We have the ability to add a server. The mechanism we have, I'll tell you exactly what we do. It's covered by these nifty little patents and things. But basically what we do is we view all of your storage as being generational. When you start up, your system and you say, I got 4 servers, we'll call that generation 0. And you distribute your data based on, let's say, transaction time. So your data is going from January 1st, 2013 through October 3rd, 2013, and you decide 4 servers now begin out. Okay. Add 2 more. We will now call this generation 2. If you get any data for something which happened in the January 1st to October 2nd time frame, we'll use one of the first 4 servers to store it, exactly the way it would have been in generation 1. If it's something which is newer, we can store it anywhere we want.
So are you guys thinking towards allowing, look towards a middle layer programming language whereby it gives sort of generational hints or other types of hints to the system so that you guys can better set up your underlying language or that kind of
I would love to hear more on that question. Right now, the answer is no. We think this is my. The reason I'm saying I'd like to hear from you about this is what we've done in this area is kind of new. The notion of saying that storage is generational was done a long time ago once for file system storage, VAX VMS time, but was never moved forward from there. When you think about it, so Terry said we should be out of here by 9 o'clock, right? So the question comes down to, we're basically talking about co-location of data for the purpose of joint performance or aggregation performance or what have you. If you partition your data into five parts, and I guarantee co-location, let's assume that I'm distributing the data based on an integer value. Okay, so let's play this game. I want to store a value of 5. I've never seen 5 before. Where should I store it? Does it really matter where I store it? No. As long as you know where to go. And I got 5 again. Now where do I store it? The same place you stored it the last time. That's the important part, right? So the question of how do you do allocation of storage, most systems use a mechanism where they say hash mod 5, where 5 is the number of nodes. The moment you do that, you pour your feet in concrete, you're dead. Okay. Same thing which you've done in other places. Okay, so how about we go about it a slightly different way, and I say, the important thing for co-location is, have I seen this value before? Yes or no? If I've seen it before, do the exact same thing you did the last time. If you've not seen it before, do whatever the hell you want. Nice solution, except it needs an infinitely large data structure. This was the problem which I've faced at 2 companies so far, and one of the reasons I started this one was this problem was really bugging the crap out of me. How do we solve this problem? And one day it occurred to me that the solution was not, have I seen the problem, have I seen this value before or not? If the answers I can give you are yes or no, your life is going to suck real bad. On the other hand, if the answers I can give you are no and maybe, life's a whole lot better. Because no is the one I really care about, because then I can store it wherever I want. If it's maybe, then I'm kind of constrained what I have to do. The moment you go into no and maybe, Bloom filters are there to help you. So you can use a Bloom filter to decide where you want to store it. Eventually, at the heart of it, that's what we would do with the generations. So with that kind of a mechanism, I can add storage nodes anytime I want. Because all I need to know is in a very, very small size data structure, determine, have I seen this before, no or maybe. And oh, by the way, that has to be an algorithm which can be done in parallel in multiple places at the same time. Knowing full well that each of these is working on a set of data structures which could potentially diverge. They're going to be mutually exclusive They can work on data structures which are diverging at any point in time, but they're still going to come up with the same answers. Because if you're not able to do that and you're going to say, well, they have to work on a shared set of data structures which are in sync, okay, you're back to a single system again. That's not a scalable architecture. So if you are building a parallel architecture, try to build an architecture where you can have your workload partitioned over multiple nodes, where the nodes can run free running relative to each other as long as possible. That's basically what we do. Okay. Quick query example. Start from table, works really easily. How do we do it? Provision one dynamic node. On the dynamic node, create a temp table called P1. All of you storage nodes out there, count what you got. Redistribute that into P1, and on the dynamic node, do a sum. MapReduce people, sound familiar? Okay. What are the benefits? You guys can read this later, it's fine. We do something called multi-tenancy, where if you have a SaaS application with 10,000 tenants, all with largely the same schema, we store them all into one schema, and we tag them with an extra column. Your application comes along and does an alter table, we'll take care of it for you. Your application doesn't need to realize that. I love benchmarks, I love pictures. Red line, native MySQL with lots of databases. Blue line, us with multi-tenancy. There is a small overhead involved, in truth, but yeah, it's small. Okay. Biggest thing, if you have more people hitting your site, you don't want your performance to go MySQL way, you want it to go linear. So for this particular task, we had 5 M1 extra large servers, or no, 5 M1 large servers, and MySQL was running on an M1 extra large. And we ended up being twice as expensive and 5 times the performance, or 6 times the performance. But linear scale is kind of important. 35 users, not really an interesting test. This is where it gets interesting. MySQL goes totally catatonic at about 800 users. Yeah, we're still doing fine. Very new information. This is from a couple of days ago. A lot of people tell me that they have to use NewSQL because you can't ingest data really fast into a SQL database. I can do a million rows a second if you want. Data looks like CDR data, so if you're familiar with what a CDR record looks like, that's what we did. 15 MySQL servers, 2 ParElastic servers doing the ingest. Native MySQL response, native MySQL rows per second. 5 ParElastic servers, or 5 ParElastic persistent nodes, 15 ParElastic persistent nodes, linear scale. And at a million rows a second, we're not even breathing hard. So the reason why, so this was done over, is this last weekend or last weekend or this past? Yeah, this past weekend. We capped out a million rows a second because in order to get MySQL to do close to 200,000 rows a second, I had to run the test driver on 2 C1X large servers, and I wanted to do an apples-to-apples comparison. The best I can do with the 2 C1X larges is this. I can do more than a million rows a second, but I'm going to have more test drivers. But then I'd have to do an apples-to-apples comparison, and then MySQL will look even worse. Exactly. Remember the picture of getting a bigger and bigger server and not getting a better performance? Yeah. There is an optimum size server and it may not be the largest server. If you can get many of those, you're probably in the best place. That's exactly what we're doing. Yeah, this isn't free. This is not the dollars and cents free part. We sit in the transaction path for every single query. Network runtime time in Amazon, 0.35 milliseconds. A query takes 15.7 milliseconds with a standard MySQL. If you were to do the same thing with us, just passing through us, the query takes 1703. Our overhead is somewhere around 1.3 millisecond. This picture is probably 6 months old. The newer version of our product, this number is dramatically lower. But
So you're saying less than 5%?
I'm not saying that because that would be disingenuous to say, because that would assume that your queries were all 15%, 15 milliseconds. If your queries are what I will say is this: if you're doing high frequency trading, don't bother with us, because this is not high frequency. This is automatically capping you at 600 transactions a second at this number. The second thing which I will tell you is this: if native MySQL under load can execute your query in 0.3 milliseconds, we're going to triple the time for your query. On the other hand, if your native MySQL under load is doing stuff in 0.3 milliseconds, you don't have a scalability problem. So if you have a scalability problem, this number is usually like 100, 200, 300. Then the 1.3 is a whole lot less than 5%. How do we characterize it? This is, maybe I should wait for this slide to tell you all I just did. How do I characterize our performance? It's basically there's a fixed cost and a variable cost. The fixed cost is 1.3 milliseconds, which we're driving down in every release. On the other hand, let's assume I put 2 billion rows in a table. This table, by the way, is the sysbench I was using for all of my tests, 2 billion rows. If I have one node, MySQL takes 968 seconds to actually count 960. Sorry, this is not milliseconds, this is seconds. It takes about 15 minutes to do that. Turn off caching, force the table scan. If we were to do that with more and more ParElastic nodes, that's the response time. Okay. The overhead is still the same. This is the amortization of that overhead over parallels. Okay. Some things to keep in mind. The only way you can horizontally scale out is if you are stateless. This is the same for us. This is the same for your application. If you can build your application to be largely stateless and not have tightly coupled state, you can scale your application horizontally. If not, maybe not. If you have complex or shared state, you're not going to be able to do that. Salesy slide, what are we? We're basically a virtualization layer for the database. From the application's perspective, don't change anything. We'll give you the ability to query all of your data exactly as it is. We're trying to go after several different markets. High traffic websites are one area. SaaS enablement is another area which we're talking about. But basically, it's how do you want to virtualize your database. If you're doing a dev test in your company, if you have a high expense on CapEx, we can probably help you drive that down. Where can you get it? You can get it on Amazon. Go to Amazon Marketplace, type ParElastic. You can get it there for free. We're giving our software away for free, and all you have to pay is the Amazon hosting fees. So that, I think, is about all I got. It says conclusion. It's probably a good idea. Yeah, sharding is not exactly my favorite thing. I unfortunately seen too many people who've gotten pretty badly burned by it over time. Some references for you, and more questions if you want.
Let's give a great big round of applause for Amrith Kumar, CTO and founder of ParElastic. Is there any questions? Yes.
So you care about, obviously you do care about the geographic dispersed servers, and how do you control that with Amazon? Because and what is considered, network close?
So, okay. Everybody heard the question? Or should I repeat it? How do we deal with geographically dispersed servers? And in Amazon, how do you actually control it? Okay. In Amazon, so first of all, can you have geographically dispersed servers? Absolutely. We have no problem with think about us as a virtualization layer above the collection of servers where they are here. The servers never talk to each other directly, so that's good. In Amazon, if you want to have them geographically dispersed, the only way you can do it is choose different availability zone. Even if you were to say, I'm in US East 1A and 1B, there's no guarantee that you're going to be in a different region. If US East 1, US West something, then you're guaranteed to perform. Part one of the answer. In the private data center context, we're working with a very large telco who has 8 locations where they're ingesting CDR data at very high speed. And they're going to ingest the data directly into the MySQL database in geography wherever that is. And from a central location, they have the ability to query all of them and get one common view of the data for some use cases. Because for those use cases, they give the query to us. We partition that query up. We send parts of it out to the underlying nodes. The underlying nodes chomp on the data on their subset. They return a small amount of data. There's a local dynamic node which accumulates that, sorts it.
So each MySQL instance is really different.
Entirely different.
Any other questions? Okay. Amrith Kumar, thank you very much.